Let's discuss some ideas about measuring, to distinguish between counting and measuring, look at the three fundamental units of measurement in examples, and determine why a measuring standard is needed, and find out about uncertainty in a measurement. The first thing we need to do is talk about counting. One of the first things a child learns to do is to count. Counting involves whole numbers, what we call integers. It ignores anything about the thing that we're counting other than its existence. So a big duck is one duck, a small duck is one duck. Examples: days until the end of the term, pages in your textbook, or number of students in your class. Counting numbers can be exact. We can't estimate 1.3 ducks. It makes no sense. It's either a duck or it's not a duck. You either count it or you don't. Now, measuring is the basis of all science. We use counting sometimes, but measurement is 90-some% of what we do in science. Measurement involves what's called real numbers, not integers. Whole units and parts of a unit are measured. So you might want to discuss with someone how old you are. If you do, you're rounding off. If you say you're 15 or 16. First you could say, I'm 15 years and 3 months, or 15 years and 2 months, and 29 days and 3 hours. But that always changes. Scientists give measurements in decimal numbers, like 14.36 years. We don't ever use rational fractions like 1/2 or 2/3 when we write a number. So that's what you should do all the time, use decimal numbers. Measurements accurately describe the quantitative properties of an object. What is the reason why we care about that so much? Why do we spend so much lab time measuring various changes in properties? Well, we do that so that we can learn something about the chemical or the object. So, for instance, in a chemical reaction, we want to know how much the mass changed. In a physical measurement, if we're measuring speed, for instance, we want to find out how much did a position change. Precision is very important. Your equipment operates correctly to give precise measurements. And just a pithy example, only one size spark plug fits your car engine. Therefore, you have to make precise measurements of the spark plug. Now, there are three fundamental units of measure in the SI or metric system. Length is one, and from length we get area, length by length, volume, length by length by length, speed, length per unit of time, density, mass per unit volume. These are all derived units derived from length. Mass is our second fundamental unit, how much stuff there is. From mass we get density, mass over volume, force, power, and energy. These are all derived units that require mass. And finally, time, the third fundamental unit. And from time we get speed, power, reaction rate as derived units from time and other things. All scientists use the SI, International Scientific or Metric System. The three fundamental metric units, or SI units, are for length, the meter, for mass, the kilogram. Chemists wanted the gram, but we bow to the physicists here. And for time, the fundamental unit is the second. Now, standardization is important. We have to agree on a unit of measuring length, for instance, if we're to work with each other. Imagine when you're building a house and you had a nice set of plans like this, Suppose you and the 15 other people working on site used your own foot for 1 foot. Well, clearly it would the house that you built would not look like a realization of that plan that you see in front of you. You have to agree on what a foot is. The next issue is uncertainty. We'd like our measurements to be as accurate as possible, but no measurement is 100% accurate. No measurement is completely certain. To get the best accuracy, we have to measure what we know, what we're sure of, and if we have, for instance, a metric ruler like this, we have to estimate the distance between the actual marks on the instrument scale to get a final digit, a final significant digit. Here's a thought experiment. And let's suppose that the object you see here is being measured with a meter stick that has no markings on it at all. We have to record all the digits we can read plus 1 estimated or doubtful digit. Well, you can see here we don't have any marks, so we can't be certain of any digit. Therefore, we may say this is, I don't know, 6/10, 7/10, 8/10 of the meter. And so we have only 1 sig dig because that is all we can do. All we can do is measure by estimation. So the object's about 7/10 as long as this meter stick. So the doubtful digit is the only one we write. There's 1 significant digit. Now, what uncertainty means and what it doesn't mean. Suppose we write down, after a measurement, that a length is 2.53 centimeters. That means we know, because we read marks, it's between 2 and 3 centimeters, because the 2 mark is on one side of the end of the object, and the 3 mark is on the other side of the object. We know it's between 2.5 and 2.6, because the 0.5 mark of the 2 to 3 length is on one side of the end of the object, and the 0.6 is on the other side of the end of the object. But that's the last marks we have. We know it's between 2.5 and 2.6, and we can see that it's closer to 2.5 than it is to 2.6. So we guess that it's 2.53. It could be a little less, it could be a little more. We just know for sure it's between 2.5 and 2.6, and that it's closer to 2.5 than it is to 2.6. That's why we wrote 2.53, but that last digit is not certain. In fact, the last reported digit in a measurement is always uncertain. Here is a balance, and you can see the number of digits after the decimal point is 3. The uncertain digit is the last one that you see. The 0 is uncertain. The last digit has a degree of uncertainty even if you read it off a digital device like this. The last digit is always uncertain. It could be a little more, it could be a little less. So, all measurements are approximations. All measurements involve some uncertainty. No instrument is absolutely accurate because no operator is perfect in its use. The accuracy depends on the precision of the measuring instrument and the skill of the experimenter when measuring. Now, what does plus or minus mean? It's a measure of the uncertainty. Let's look at this situation. Suppose we see this is a balance, one of those balances that's got 2 pans on it, and we write 32.00 grams plus or minus 0.02 because that's the uncertainty in the instrument. We say that the mass reading is 32.00 grams. However, because of the imperfection of the instrument, the real mass could be as high as 32.02 grams. The real mass could be as low as 31.98 grams. It's certainly between those two numbers. Suppose if we used a more accurate balance, we found out it was 31.9963 grams. That's between those two numbers. So that is a measure of the uncertainty of this particular measurement, and it's going to be governed by the uncertainty in the instrument. Calibration will improve accuracy. With calibration, we adjust the instrument so its reading is consonant with a standard measure. So, for instance, we put a 1 gram standard mass on one of those electronic balances, and then we adjust the reading on the balance so it reads 1.000 gram. What would happen if we adjusted the balance to read 1.5 grams? You might want to turn the video and talk to somebody about that. Turn it back on later. Well, our readings later on would be too what? Small or big? Well, the answer is, since we calibrated it high, they would be too big. So you might want to practice, give an example of a count of people and a measurement of a person. Indicate the doubtful digit in the measurement you see here. Write down what determines the accuracy of a measurement, and always be able to give a 1-sentence or 2-sentence explanation of why we need standard measures. Now, the SI prefixes are important because they modify the units of the SI system. We apply them to the basic unit. You've probably done this for years. So if we want to say 1,000 meters, we can say 1.000 kilometer. So what is 1,000 grams? It's 1 kilogram. Here are the SI prefixes. Let me show you the critical prefixes in chemistry. Are kilo, 1,000 or 10 to the third, deci, which is 0.1 or 10 to the negative 1, centi, which is 0.01 or 10 to the negative 2, milli, 10 to the negative 3, and nano, 10 to the negative 9th. We measure length by subdividing the meter into 100 centimeters, 1,000 millimeters. So, turn the video off and figure out how many millimeters are in a centimeter. And of course you can multiply the meters, so 1,000 meters is a kilometer. Area is not often used in chemistry. It's derived from length, so the area of a rectangle. Volume is frequently used in length. In chemistry, it's derived from length. So volume 1 meter on an edge is a cubic meter, and a cubic decimeter is a liter. Mass is measured in grams in chemistry, and we frequently measure in thousandths of a gram or a milligram. And finally, a critical principle. Always remember this. When you're converting from one unit to another, remember that a statement like 1 kilometer, is 1,000 meters. Those are definitions. Those are exact equalities. There is zero uncertainty about a definition like this. And I guess I need to change this slide so it says 1,000 meters is a kilometer. See you next time.